This tutorial goes through sections 1.1 through 1.4 in the algebra textbook. The first topic we'll cover should be a summary of something we did in class, and that is expressions versus equations. Equations show that two things are actually equal to each other. So here's an equation, 5 plus 2 equals 7. This equation is always true. Here's another equation, 15 equals 3x plus 6. That equation is only true for some values of x. And another equation, y equals 3x. Whether or not that equation is true depends on both what y is and what x is. X and y have to have certain values in order for that expression to be true. Solutions to an equation are the numbers that you can plug in for the variable that make the two sides actually be equal to each other. So in the middle equation here, the solution is that x has to be 3. In order to check that that works, you can replace the x in the equation with a 3. And you'll see that you have 3 times 3, which is 9, plus 6, which is indeed equal to 15. For the third equation shown above, there are multiple different solutions because there are lots of different combinations of x and y that make the equation be true. For example, if x is 1 and y is 3, then that equation is true. If x is 2 and y is 6, that equation is also true. And we can see that we can keep going essentially forever with that. Expressions contain operations, numbers, and/or variables. So a constant expression like 5 plus 2 contains only numbers. A variable expression like 5x plus 2 contains both constants, the number 2, and variable terms, the term that has the x in it. We can have even more complicated expressions like x squared plus 3x plus 2 that have multiple different mathematical operations, in this case both raising a variable up to a power, x squared, and adding and multiplying. You can find the value of an expression for different values of the variable. So I can plug in different numbers for the variable x in the equations above, and in those expressions above, and those expressions will take on different values. For example, in the middle expression, when x equals 2, then the value of the whole expression is 12. When x is 3, the value of the whole expression is 17. In the expression on the right, if I plug in a 1 for x, then the value of the whole expression is 6. I get that by replacing all of the x's in the expression with 1's and then simplifying. When x is negative 1, the value of that expression is 0. In section 1.1, we are evaluating expressions, so you'll see problems that say things like evaluate this expression when x equals 2 and when x equals negative 2. What that means is that we're going to run the same problem twice. The first time through, we're going to plug in 2 for x. The second time, we're going to plug in negative 2 for x. When x equals 2, here's what this looks like. We replace each of the x's in the equation with the number 2, and then we use order of operations to simplify this. So 2 squared is 4, that's the exponents part. 6 times 2 is 12, that's the multiplication part. And then when we add all three of these together, 12 plus 2 is 14, plus 4 is 18. We can also evaluate the expression when x equals negative 2. And again, in this case, we replace each of the x's in the expression with a negative 2. When we do that, 6 times negative 2 is negative 12, and negative 2 squared is positive 4. Then, when I add those three terms together, I get a total of negative 6. So you can see the expression took on a different value depending on what I plugged in for x. In section 1.2, we review the order of operations. Remember, the order of operations is PEMDAS. The P says first evaluate expressions inside the parentheses. The E says to evaluate any place where you have exponents. Multiplication and division are on equal footing and are done from left to right through the equation. Then addition and subtraction are on equal footing and done from left to right throughout the equation. So if we take this expression here and simplify it using order of operations, first we'll have to look inside the parentheses. 2 plus 3, the expression inside the parentheses, can be simplified to 5. We have a second set of parentheses here. We call these nested parentheses. You notice we have the sort of rounded ones and then the squarish ones. So now we need to look at the expression inside the squarish parentheses. 13 minus 5 is 8. So now we've simplified everything inside the parentheses as best we can. Next, we evaluate the exponents. That exponent of 2 goes on the number 8, so we have 8 squared, which is 64. And then we'll multiply. 3/4 times 64 gives us 192 over 4. If we simplify that expression, we get 48. Reduce that fraction, which is really a division problem, we get 48. In your notes, please evaluate the expression that's shown below when b equals 3. Please do show your work, and then when you show me your notes in class, we'll look at this together. The next section deals with turning verbal statements, that is things that are described in words, into mathematical expressions. The table that's shown here is in your book, and I would suggest not copying the entire thing down. Rather, focus on things that you may have gotten wrong on your pretest or ones you know you have trouble with. Common things to confuse in this are confusing subtraction and division. That word difference, for example, whether that means to subtract or divide, and quotient can be a little tricky. The other thing to highlight is that order is important for both subtraction and division. For example, if a phrase says the difference of a number n and 6, we write this as the first number. The difference of a number n and 6, we take the first thing, n, minus the second thing, 6, and not 6 minus n, because those two expressions, n minus 6 and 6 minus n, don't have the same value. Likewise, when we say the quotient of a number k and 2, the k goes on the top and the 2 goes on the bottom. This isn't because the variable always goes on the top or because the constant always goes on the bottom. This has to do with the way that we phrase things when we use the words quotient and difference. Our next topic is unit rates. The word per means for each one or for everyone. So if I give out 3 chocolate bars per person, that's 3 chocolate bars for each person. $3 per dozen just means that it costs $3 of every dozen that you're buying. $12 for 4 dozen is the same unit rate as $3 for every 1 dozen. So if I bought 4 dozen cookies and I paid $12 and I was going to be charged the same rate, but I only wanted 1 dozen cookies, they should only charge me $3. If I ask you to find the unit rate, let's say that we have 32 students to be divided into 4 groups. What we're going to do is we're going to do the number part of this division problem first. 32 divided by 4. 32 divided by 4 is 8. And then it's as though we stack our units into a division problem. Students over group. Students per group. So our unit rate is 8 students per group. 8 students per 1 group. Here's an example that pulls together some of the things we've looked at. This example has to do with cell phones. Your basic monthly charge for cell phone service is $30. You pay that $30 whether you talk or not. And the first 300 minutes of your talk are free. They're included in that $30 fee. Then you pay a fee for each extra minute that you use. In one particular month, you paid $3.75 for 15 extra minutes. The question is, if in the next month you use 22 extra minutes, what will your total bill be? So the first thing we need to do is to find the unit rate. What is the cost per minute in this problem? Well, we know that we paid $3.75 for 15 extra minutes. So we can find the rate in dollars per minute. $0.25 per 1 minute. I took $3.75 and divided it by 15, and I got 0.25 over 1, or 25 cents per minute. Next, I want to write a verbal model and then turn that into mathematical expression. If M is the number of extra minutes that I talk, then the total amount of money that I'm going to have to pay is a combination of two things. The basic charge in dollars, and then the extra cost for the extra minutes. The cost for the extra minutes is the rate times the total number of extra minutes. So 0.25, that's 25 cents per minute, times the number of minutes. We can use dimensional analysis to check to make sure that this expression makes sense. The unit on the basic charge is dollars. The rate for those extra minutes is dollars per minute, and we're taking dollars per minute and multiplying it by minutes. The minutes on the bottom and the minutes on the top cancel out, and I'm left with dollars. And so the units of our answer are dollars. Next, we're going to evaluate that expression. We built this mathematical model to tell me the cost for M minutes. I want to know the cost when M is 22, the cost for 22 minutes. So I take my expression and I plug 22 in for the M. I simplify that expression and I get that the total bill is $35.50. Hey, here's some random trivia. Top 3 music selling albums of all time. Thriller, still #1. Pink Floyd's Dark Side of the Moon, which has spent the longest of any record album in history on Billboard's Top 100 chart. And AC/DC's Back in Black, a pretty awesome album. So there's your random trivia for the day. All right, back to math. Inequalities. Inequalities. There are 2 good ways to remember which way the inequality symbol is pointing. One is to remember that the bigger side of the symbol points towards the bigger number. So here's an inequality symbol, and it has a big side and a little side. The bigger number should be on the bigger side. 5 is the bigger number, so 5 goes on the bigger side of the inequality. 3 is the smaller number, so 3 goes on the smaller side. Another one, and you may have remembered this from when you were in grade school, is we make that inequality symbol into a mouth, we give it some teeth, and it wants to eat the bigger of the 2 numbers. I'll admit to you, this one always seemed a little small to me, because in my mind, it was like the little number was eating the big number, which always seemed kind of weird, but if this one works for you, more power to you. So again, the bigger number is the one that the mouth is eating. Okay, so kinesthetic inequalities. If you're a kinesthetic learner, it might help you to use your arms in the air to make an inequality symbol pointing in the correct direction. So I'm going to flash you some pairs of numbers, and you're going to go ahead and make yourself the correct symbol in between them. If you're sitting at a computer watching this, you might just hold your fingers up to make the right symbol. So in this case, which is bigger, 4 or -8? 4 is the bigger number. Remember, 8 is in this case is negative, and so that's much further down the number line. Between 6 and 12 thirds, that's 12 thirds, not 1 and 2 thirds. Well, if I took 12 thirds and I simplified it, 12 over 3, that's 4. So 6 is the bigger of those 2 numbers. Next, if I had -14.5 and -14, which of those is bigger? Be careful. You might think to yourself, well, 14.5 is bigger than 14. But because these numbers are both negative, remember we're thinking about which one is further right on the number line. That's the bigger one. In this case, -14 is a bigger number. It is not quite as negative as -14.5. And 4 and -8, gee, this feels like we've done this one already. 4 is the bigger of those two. All right, what happens when we start putting variables in inequalities? So here's an inequality. X is greater than 8. What are some numbers that I could plug in for 8 to make this inequality be true? Well, X could be 9 or 10 or a million or 8.00001. X could be anything bigger than 8, but not 8 itself, and it certainly couldn't be smaller than 8. So there's a lot of different numbers that make this expression true, but not every number makes this expression true. Some additional inequality symbols you'll want to know about. So here what's shown is x is greater than 8. If we add another line underneath that, the way you read this out loud is x is greater than or equal to 8. That means that x can be any number that's bigger than 8, but it can also equal 8 itself. So the solutions to this inequality are numbers that start at exactly 8 and get bigger and bigger from there. What are some real-life situations we use inequalities to model? Well, here's one. We used to have a policy that the highest score you could get on a retake in a math test was an 89. So if S is your score on the retake, then S is less than or equal to 89. In your book, you'll see this chart that helps you understand the connections between certain words in word problems and the mathematical symbols. Be careful because things like fewer than or at most or no more than can get a little bit confusing, so you may want to copy this table down into your notes, or you may just want to refer back to it as you're working through word problems.